Hi everybody. Today I want to continue our study of Chapter 1 in Schroeder and discuss thermal expansion and then how to convert between moles and mass. So first let's talk about thermal expansion. Thermal expansion is defined as the increase in the size of an object caused by an increase in the temperature. Now, why does this happen? Well, if you think about a solid, for example, then the atoms are sitting in their equilibrium positions and they oscillate about those equilibrium positions at a given temperature. But as the temperature increases, what happens is, if you look at this potential energy function here, you can see that it's skewed to the right, okay? So as the temperature increases, the average spacing between those atoms moves right due to the shape of that potential energy curve. A physical way to think about it is because as the atoms are vibrating about their lattice positions, the amplitude of oscillation will increase as the temperature increases. And then because the amplitude of oscillation is increasing, that physically means that the atoms probably have to move a little further apart as they vibrate at higher amplitudes. Now, most of the time, we can't tell that this is happening just by looking at it. We have to have a pretty sensitive measuring device in order to see it. And that's because generally the expansion is small relative to the original dimensions of the object. Now, this also means that since the expansion is small, we can approximate it as linear as long as the temperature range that it changes over isn't too big. Now, it's important to note, there's lots of fun demos that I'll do in class about this, but if you heat an object up, it's important to note that not only the mass, part with mass, but also holes, any holes or voids in the object will also increase in size as the temperature increases. Now, the equation for linear expansion is usually defined in terms of the coefficient of linear expansion, which many texts refer to as alpha. Alpha is defined as the change in the length of an object, delta L, divided by its initial length, and then that ratio divided by the change in temperature, delta T. A convenient way to write this equation is usually delta L is equal to alpha Li delta T. It's also kind of interesting to note that you can approximate it as linear over any one dimension for objects that we consider to be either polycrystalline or amorphous. What that means is that not all of the atoms in their lattice positions are going to line up in exactly the same direction. You might have some regions where the lattice crystalline structure lines up in one way, and then right next to it, it's all rotated in another direction. This causes the change in the length with the increase in temperature to be the same no matter whether you're measuring in the X, the Y, or the Z. And it's just because the atoms aren't all oriented in the same direction throughout the material. They're not uniform. However, if you have a single crystal or monocrystalline material, then you might notice that the coefficient of linear expansion is different in different directions. And this is because of the crystal structure of the materials themselves. And so if you look along one crystalline axis, you might have a larger expansion for the same temperature than you do in the other direction. One example of this is antimony. Its coefficient of expansion along the trigonal axis is twice as large as when you look at the axis that's 90 degrees to that. So that's kind of interesting. And it just has to do with how the atoms are oriented in the crystalline lattice. Some single crystals are symmetric, like the salt image pictured here, while others might not be the same due to the way the crystal is structured. But that's more of a topic for material science and isn't really something that I want to get into today because it's a little complicated. Now, we can also talk about the volume expansion of a solid or a liquid. The change in volume is proportional to the original volume and to the change in temperature. The equation looks very similar to the coefficient for linear expansion when we write it out. Delta V is equal to beta V sub I delta T, where delta V is the change in volume, beta is now defined as the coefficient of volume expansion, Vi is the initial volume, and delta T is the change in temperature. For solids, beta is equal to 3 times alpha to a linear approximation, and so it's a good approximation for most times. This is if the material is isotropic, when it's the same in all directions, which, as we just discussed earlier, for single crystal materials might not be the case, but works most of the time for most materials. Now, if you're talking about a liquid, then beta isn't going to be equal to 3 alpha because it doesn't really make too much sense, first of all, to talk about a linear dimension of a liquid anyway. They generally fill whatever container they're in and take that shape. So it's better to just talk about how the volume changes with temperature. So if you look in tables of data for volume and linear expansion coefficients, you're not going to really find alphas listed for liquids. You're only going to find betas. We can also define the change in the area as an object is heated, and that, as you might guess, is written as delta A equals 2 alpha AI delta T, where delta A is the change in area, alpha is the linear expansion coefficient, AI is the initial area, and delta T is the change in the temperature. Here's some common coefficients that are listed. You can see that for solid materials, these are on the order of 10 to the minus 6 per degree C. And then for volumes, they're on the order of about 10 to the minus 4, 10 to the minus 3, 10 to the minus 4 inverse degree C. Let me do an example problem for volume and area expansion. So here we have a 1 liter glass flask and it's filled to the brim with alcohol. It's initially at 10 degrees Celsius. If the temperature warms to 30 degrees Celsius, how much alcohol spills out of the flask? Okay, so we're assuming here, like it says, that the 1 liter flask is filled to the brim, which means that if you heat it up, any expansion in the volume will cause the container to overflow. So we need to remember the equation for volume expansion. Delta V is equal to beta VI delta T. So what we need to do is we need to solve for both the flask and the alcohol, and then take the difference in those two numbers to see how much alcohol is going to spill out. Because remember, the volume of the glass flask will change a little bit too. It'll expand as well. But because the expansion coefficients for solids are generally smaller than the expansion coefficients for liquids, the liquid will expand more than the solid and you'll lose some liquid. So let's solve this. Okay, so for the glass, we can read off from some tables and get the linear expansion coefficient. And then we multiply that by 3 to get the volume expansion coefficient. So if we do that, delta V would be 3 alpha VI delta T, which is 3 times 9 times 10 to the minus 6 inverse degree C, which is the linear expansion coefficient for glass, times the initial volume, which is 1 liter, times that change in temperature. The temperature rose from 10 to 30 degrees C, and that's a delta T of 20 degrees C. When you multiply all those numbers together, you get 5.4 times 10 to the minus 4 liters, or 0.54 milliliters. That's how much the glass expands. Now for the alcohol, the equation is delta V is beta VI delta T, but of course for a liquid, we're given beta directly. We don't have to calculate it. So if you read that off from a table, beta is 1.12 times 10 to the minus 4 inverse degrees Celsius, VI is again 1 liter, and delta T is again 20 degrees C. If you multiply those numbers together, you get 2.24 milliliters. So if you subtract those two numbers, 2.24 milliliters minus 0.54 milliliters, then you can get the amount of alcohol that will spill out of that flask. And you find that 1.7 milliliters spills out. Okay, so that wraps it up for thermal and volume expansion. Now let's talk about how to convert between the number of atoms, moles, and masses. This is really important when we start talking about the ideal gas law. So first let's talk about the mass of an atom. The mass of an atom is determined primarily by the protons and the neutrons that are in a nucleus. Of course we should count the electrons too, but because they're 1,000 times less massive, they really don't have as much of an impact. The sum of the mass of the protons and neutrons, minus the binding energy, which we'll get into in modern physics, is called the atomic mass, A. Now, our atomic mass scale has been established by defining the mass of a carbon-12 atom to be exactly 12 atomic mass units. I often abbreviate atomic mass unit as U, but sometimes it's abbreviated as AMU in some textbooks. So I'm going to use U for the symbol of atomic mass unit. To convert between atomic mass units and the SI standard of mass, which is the kilogram, one atomic mass unit is 1.66 times 10 to the minus 27 kilograms. Now these are tiny little masses, which makes the atomic mass unit a more convenient unit for discussing mass of nuclei and atoms. Now, it's interesting to note that you can read a lot of the important numbers that you'll need to do these problems straight off most periodic tables. So if you look at the periodic table, for example, this is a common looking periodic table block for carbon here, which is abbreviated with the C. Z is the atomic number, and that's the number of protons. It's also equal to the number of electrons if it's a neutral atom. So we know that there's 6 protons and 6 electrons in a neutral carbon. So that's usually indicated. The atomic mass number is also generally indicated right here. You can see A is 12.011. Now you might notice, or you might think, that since we've defined carbon-12 to be exactly 12, why is that number not exactly 12? Well, that's interesting, and it has to do with the various isotopes of carbon. So not all carbon is carbon-12. We have some carbon-13, and we also have some carbon-14, which is, of course, radioactive. Okay, so the number displayed as the atomic mass in the periodic table is usually an average value over all the isotopes. It's a weighted average because not all the isotopes are equally likely, and that's why it's pulled closer to 12. All right. Now, by definition, 1 mole of matter, be it solid, liquid, gas, or whatever, is the amount of that substance containing the same number of constituents as there are atoms in 12 grams of carbon-12. This is called Avogadro's number, which is 6.022 times 10 to the 23rd. So if you have 6.022 times 10 to the 23rd of anything, you have 1 mole of it. So you can have a mole of moles, although that would be really terrible, as you might know, if you figure out what would happen. So you can go online, what happens if you had a mole of moles, and you can see the disastrous consequences of that. But anyway, you can calculate the number of moles in a substance just by dividing the number of basic particles that you have by Avogadro's number, and that'll give you the number of moles. Now, you can also figure out from the mass of the sample that you have and the mass of one atom, how many atoms you have. So if your atomic mass is specified in kilograms, then the number of atoms in the system of mass big M can be found from dividing the total mass of the system by the mass of one atom. And that'll give you the number of atoms that you have, big M. Now, if you want to find the number of moles of that, of course, you would then divide big N by Avogadro's number, and you'd have the number of moles. But you can also figure out the molar mass of a substance, okay? So the molar mass of a substance is the mass in grams of 1 mole of that substance. We're going to use here the molar mass as big M sum MOL, which stands for mole. Now, the number of moles in a system of mass big M consisting of atoms or molecules with molar mass big M sub mol is equal to little n, where n is equal to the mass in grams big M divided by the molecular mass. So, if you have 300 grams of something and you know that your molecular mass is 50 grams, then you know that you have 300 divided by 50, which would be 6 moles of that substance. Now here's an interesting trick of units that we actually engineered. So 1 atomic mass unit is 1.66 times 10 to the minus 27 kilograms. If you express that instead in grams, you get 1.66 times 10 to the minus 24 grams. If you take the inverse of that mass, then you get Avogadro's number. And that's because we've defined Avogadro's number so that 1 mole of carbon-12 gives you 12 grams of mass. So it's no coincidence that these numbers work out that way. So what this means is that the atomic mass given on the periodic table, here's the periodic table entry for copper, okay, which has 29 protons. So you can read off the atomic mass, 63.546, and that's the average atomic mass for 1 atom of copper in atomic mass units. But because of the way that we've engineered the units, it's also the mass in grams for 1 mole of the substance. So if you have 1 mole of copper, pure copper, then you have 63.5 grams of it. Okay? Now, most periodic tables don't report quantities like density, for example. And that's because it depends on specific physical conditions like the temperature, pressure, and the phase. So you'll be able to read off the molecular mass, you'll be able to read off the number of protons or electrons in a neutral atom, but things like density aren't going to be given, and you'll have to look them up in a table. Okay, let's talk about an example problem here. So, how many moles of methane, the chemical formula of that is CH4, which means that there's 1 carbon and 4 hydrogen atoms in one molecule. How many moles of methane are there in 52 grams of this gas? So this is a common kind of conversion that you have to do for ideal gas problems. Okay, so to figure this out, you look at the periodic table and you get the atomic mass read off the periodic table. So we talked about carbon already. It's got 12.011 grams per mole of carbon. And if you read off for hydrogen, it's got 1.0079 grams for 1 mole of hydrogen. So to find the mass of 1 mole of methane, you just take 12.011 for the 1 carbon plus 4 times 1.0079 for the 4 hydrogens. You sum that to get 16.0426 grams for 1 mole of methane. Now, in order to find the number of moles, you just take the mass of the amount that you have, which here is given as 52 grams, and you divide that by the molar mass, which is 16.0426 grams per mole, and you solve, and you get 3.24 moles in 52 grams of methane. Okay, so that leads into our next lecture, which I'll do in a separate video, discussing the ideal gas law and some simple applications of that. So thanks for watching, and I'll see you next time.